So in this video, we're going to explore what we mean by the conjugate of a complex number and then develop some of its properties. So the first thing we should do is define what a conjugate is. So if we have a complex number z, suppose it's x plus iy, remember x is the real part of z and y is the imaginary part of z, then the complex conjugate we denote by z bar. We put a bar above it, and we have the same real part, but we have the imaginary part being the opposite sign to the original imaginary part. So if we, and the term we're using is conjugate. So z bar is the conjugate of z, x minus iy compared to x plus iy. So we'll notice that we've got various elements here. We've got the real part of z being x, real number x, the imaginary part of z being the real number y, the real part of the conjugate of z is still x, and the imaginary part of the conjugate, z bar, is negative y. So we can state that the real part of z bar, the conjugate of z, is exactly the same as the real part of z. And the imaginary part of z bar, that's this, is the negative of the imaginary part of z. So there's a couple of relationships between real and imaginary parts of a complex number z and its conjugate z bar. So here's some examples for you to try. I'm going to give you 4 complex numbers. 2 plus 3i, negative 3 minus I, negative 2i, and 4. And we'll call that complex number z. So you have to find out z bar, the conjugate. You have to work out the real part of z, the imaginary part of z, the real part of z bar, and the imaginary part of z bar. So try that now, see how you get on, and we'll compare answers. Okay, so 2 plus 3i, complex conjugate of that would be 2 minus 3i. So the real part of z was 2, and the imaginary part of z was 3. If we now look at the conjugate, the real part of the conjugate is 2, same as the real part of the original complex number z. The imaginary part of z bar is the part that's changed. It's now the negative of the original imaginary part. So real parts are equal, imaginary parts are opposite signs. Let's look at negative 3 minus I. The complex conjugate of that would be negative 3 plus I. So we start out with negative 3 minus I, where the real part's minus 3 and the imaginary part is minus 1, minus 3 and minus 1. And the conjugate, the real part's the same, but the imaginary part is of opposite sign. So two imaginary parts now of opposite sign, the real part's still the same. Negative 2i, complex conjugate of that. Now the real part of this is 0. So it would still be 0 in this. The imaginary part would have opposite signs, so it would be positive 2i. So 2i is the complex conjugate of minus 2i. Real part of the original number z is 0, imaginary part is minus 2. Real part of the conjugate is still the same as 0. The imaginary part, opposite sign, it's now 2. So negative 2 and 2, opposite signs for the imaginary part. And this that's a purely imaginary number, negative 2i. This is a purely real number. The imaginary part is 0. So the real part remains the same. There's no imaginary part to change the sign of. It's just 0. So 4 is its own conjugate. Real part of the original number is 4, imaginary part 0. The real part in the conjugate doesn't change. The imaginary part changes sign, but if it's 0, it stays as 0, obviously. So how did you get on? I hope that was of benefit and it made the ideas slightly clearer. So let's move on and explore some of the properties. One of the first things, here's one maybe you should explore before we get going, is have a look at z plus z bar and try and figure out what the relationship is between z plus z bar and the real part of z. Now you might like to try that with a couple of examples. For instance, let's choose 2 plus 3i and a second number 3 minus I. So if you stop the video just now, work out z plus z bar, look at the relationship between your answer, the complex number that you get for this, and the real part of z. See what the connection is there. So stop the video and try and explore that. Okay, how did you get on with that? 2 plus 3i plus its conjugate 2 minus 3i, you'll notice the imaginary parts vanish and you get 4. Now, the real part of 2 plus 3i was 2. We've added a couple of them together, so this really is twice the real part of z. I hope you noticed that. 3 minus I, similar sort of thing. If we add the conjugate 3 plus I, we'll get 6. And the imaginary parts disappear. 3 plus 3 is 6. 3 is the real part of the complex number. So 6 is twice the real part of z. So that's the exploring of 2. Let's try and prove that in general and see how we get on. So let's prove that z plus z bar is twice the real part of z. So here's the proof. Well, first of all, let z be very general. We're doing this for every single complex number, so we have to write down a general complex number, which we'll say is x plus iy. Remember, x and y are real numbers. So let z be x plus iy. Then its conjugate will be x minus iy. When we add these two complex numbers together, x plus iy plus x minus iy, we get twice x and the imaginary parts cancel. Now we know that the real part of z is x, so this is twice the real part of z, and that's our proof completed. Now one for you, let's clear this, and one for you to explore. Just explore the relationship between z minus z bar and the imaginary part of z. So what is the relationship? And again, I would suggest that what you do is have a look at a couple like 2 plus 3i and 3 minus I and see what you can discover from that. So if you stop the video and explore that situation. So how did you get on with that? Let's have a look at 2 plus 3i. And we're subtracting its conjugate, which is 2 minus 3i. Get rid of brackets. Minus 2 plus 3i. You'll notice in this case the real parts vanish and the imaginary parts we're adding to get 6i. Now you have to be a bit careful here when you're working out a relationship. If we call 2 plus 3i the complex number z, then z minus z bar is this. Call this z. Then the imaginary part of z is the real number 3. So this real number 6 is twice the imaginary part of z. But we've still got a times I sitting there. So you may have got confused there. But let's have a look at the other complex number. This time 3 minus I, or let's call it w, so that we don't get confused with the z that we had. 3 minus I, and then we're subtracting its conjugate, which is 3 plus I. Again, get rid of brackets. We'll have minus 3 minus I. The imaginary parts cancel, and the real parts cancel, and the imaginary parts minus I minus twice I. And then if we look at the imaginary part of w, it's the number -1, the real number -1. So this real number -2 is twice the imaginary part of the complex number w. And we've still got a times I sitting there. So I think what we should be trying to prove in this case, and what we've discovered, is to prove that for a complex number z, if we subtract its conjugate, then we're ending up with 2i times the imaginary part of z. And that, I think, would be the relationship that we would be trying to prove in this case. Now, again, you might like to try this yourself in the general case. Otherwise, I'm just going ahead to prove this. But if you want, just stop the video and try and prove that in the general case. So here's the proof. We'll let z be the complex number x plus iy. Then we know its conjugate will be x minus iy. So we know it's the difference of these two complex numbers, x plus iy minus x minus iy, will be given by 2iy. The real parts cancel. Iy plus iy gives you 2iy. Now we also know that the real part of z is x, and the imaginary part of z is y. We know the real part of z bar is the same, x, and the imaginary part of z bar is the negative, that's minus y. So here we have twice the imaginary part of z, which is the number y. There's twice the imaginary part of z, that's 2y times the I. So it's 2i times the imaginary part of z. And that's our proof. Now, another example that you might like to tackle. So you might want to stop the video and try this proof. We're going to prove that if you have a conjugate of z, then the conjugate of that is equal to z. Stop the video, see if you can tackle that. So, deceptively simple, but we will need to be careful what we write down. Again, you must start by saying that this is very general. We'll let z be the complex number x plus iy. And we can display its conjugate. That's x minus iy. So having established that, we now know that we have to find the conjugate of this conjugate. Now previously I demonstrated that if you have a Cartesian form of a complex number and you want to show the bar for its conjugate, we put it over the whole thing. So it's the bar of x minus iy, the conjugate of x minus iy, which you keep the real part as it is, and the imaginary part, the minus y, changes sign, so it becomes plus y. So plus I, y. And then if we look up here, we see that we're back to where we started. So the conjugate of a conjugate is back to the original complex number. So one last thing. We'll move on now to seeing how conjugation of surds is connected to addition, subtraction, multiplication, and division. So I think this is probably property 4, if I've been numbering them correctly. So the first part of this would be to look at the sum of two complex numbers and try to determine what the conjugate of that is. Now you may well suspect this one, and you would be right if you suspect it's the sum of the two conjugates. We'll have a look at the proof of these in a minute. The difference of two complex numbers, and we find the conjugate of that, we'll find it's just the difference of the two conjugates. Now it would be nice if similar properties hold for multiplication. Is the conjugate of the product of z1 and z2 the same as the product of the two conjugates? We'll find out that's also true. And similarly, is the conjugate of the division of z1 and z2 the same as what we would get by dividing the two conjugates? So there's 4 properties that we might like to try and prove. Let's have a look at the proof of the first one. How we would do this is to say, in general, let's call z1 x1 plus i1, that's a general complex number, and let's take z2 as any complex number. Now you might like to stop the video and see if you can continue the proof. So let's look at z1 plus z2 adding these two complex numbers, we get real part x1 plus x2, and we get imaginary part y1 plus y2. And if we're looking at the conjugate of that, then we're looking at the conjugate of that complex number, which we know the real part will be the same and the imaginary part will be opposite sign. Now, we can look at this complex number and split it. Just let me get rid of the second set of brackets. There's x1 minus i1, and there's x2 minus y2. So it's just a rearrangement of all the parts that constitute this expression. Now, you can see that x1 minus iy1 is just the conjugate of z1. And you can see that x2 minus iy2 is just the conjugate of z2. So there's the proof of the first part. Now I'll leave it to you to try and prove the second part of this series of properties. And I'll go on and try to prove this product rule. So let me just wipe out this to give myself some space. And again, we start off by saying let z1 and z2 be the complex numbers x1 plus iy1 and x2 plus iy2. Now it's slightly more complicated this time, so let's look at z1, z2, and we're going to conjugate that. x1 plus iy1, x2 plus iy2. Now remember, you can stop the tape and concentrate on what's going on. You might like to try this yourself and see how you get on. x1, x2 minus y1, y2 is the real part of that product. You can check that. Plus I times x1, y2 plus y1, x2. It's the imaginary part. And we have to find the conjugate of that. So that'll be x1, x2 minus y1, y2. Real part is the same. And we make the imaginary part the negative of that. And I'm going to multiply out the brackets here, if you like. Get rid of the brackets. So it's x1, y2 minus I, y1, x2. So let's now look at the individual conjugates and what we would get by multiplying them. So the conjugate of z1 is x1 minus iy1, and the conjugate of z2 is x2 minus iy2. So multiplying these two out, real part is x1, x2, which we do have here. And the other part of the real part of this would come from the last twos. There's a positive I squared y1, y2. So that's your minus iy1 times minus iy2. Negative and negative is positive. I squared y1, y2. And remember, I squared is negative 1. So we have a minus y1, y2 coming in, which is that. The imaginary parts are coming from minus I x1, y2. That's the outside two terms. So that's minus I x1, y2, which is certainly that. And the inside two, minus I y1, x2. Minus I y1, x2, which is certainly that. So we have shown that individual product of the conjugates is the same as the conjugate of the product. Hence the result. So that leaves that. Now, the way I'm going to tackle the last part of this proving it is not go into the very general case, but what I'm going to do is just look at the reciprocal of Z2 and see if we can prove the result for the reciprocal. So I'm basically looking at Z bar Z1 divided by Z2, the conjugate of that. I'm going to be looking at Z1 times the reciprocal of Z2. So I mean, this harks back to the fact if we're dividing 4 by 2, it's the same as 4 times a half. That's the reciprocal of 2. This is a similar sort of thing that we're doing here. And since these are both complex numbers, we've already proved that the conjugate of a product is the product of the two conjugates. So I know from part 3 that this is the conjugate of Z1 times whatever the conjugate of 1 over Z2 is. So we're needing to say, answer this question: is the conjugate of 1 over Z2 the same as the conjugate of 1 over the conjugate of Z2? Conjugate of 1 being just 1, in other words, is this the case? And if that's the case, what we can do then is to say, well, we've got Z1 bar times 1 over Z2 bar, which we know is Z1 bar over Z2 bar, and hence the result. So we really have to show that the conjugate of 1 over Z2 is the same as 1 over the conjugate of Z2. So we'll let Z2 be the usual, it's x2 plus I y2. We know that 1 over x2 plus I2 y2 can be sorted by multiplying top and bottom by x2 minus iy2, that's the conjugate of x2 plus y2. So we're ending up with x2 minus iy2 over, the real part of this is x2 squared, the minus I squared y2 squared, which is plus y2 squared, and the outsides and insides cancel, the imaginary part disappears, so that's a real number. And if we're looking at the conjugate of this, which would be the conjugate of this, which is the conjugate of this, then it'll be x2 plus iy2. Each of the x2s and y2s are divided by this real number x2 squared plus y2 squared. So that's the final complex number that we get when we divide 1 by x2 plus y2. The real part is x2 over x2 squared plus y2 squared. The imaginary part is y2 over x2 squared plus y2 squared. And all that remains now is to do a similar sort of calculation for 1 over z2 bar and see that we get the same thing. Now z2 bar is x2 minus, it's a conjugate, so it's x2 minus iy2. We multiply top and bottom by x2 plus y2. So we end up with x2 plus iy2, and this times its conjugate, the real part is x2 squared, the imaginary part is y2 squared as before. Sorry, the real part is x2 squared plus y2 squared, the imaginary parts cancel. So we're left with two equal things. So we certainly know that the conjugate of 1 over z2, we've just proved that that's equal to 1 over the conjugate of z2. And that is the conjugate of z1 divided by the conjugate of z2. A bit messy, but we eventually got there. Now, it'd be well worth your while, if you're really wanting to get proficient with this, try this yourself. This is not an easy proof. It's messy, there's a lot of technical bits in it, the algebra's quite heavy, but certainly that's the result. So let's just wipe all that out and have some fun, a bit lighter for the rest of this. So, an example for yourself. See if you can prove that Z equals Z bar means that Z is a member of the real numbers. See if you can do that. Okay, let's tackle that. So we'll let Z be x plus iy. Its conjugate is x minus iy. We're told these are equal. So that means that x plus iy is the same as x minus iy. Now, two complex numbers being equal, the real parts must be equal, the two x's are equal, but it also implies their imaginary parts must be equal, so y must equal negative y. Now, they're real numbers. Let's add y to both sides. And the only possibility, twice a number is 0, the number must be 0. So we've ended up showing that z is of the form x. Imaginary part has disappeared. Imaginary part is 0. And that's a real number. So if a number, complex number equals its conjugate, then it must be a real number. Now, it's also true the other way around. This would mean that we could put a double-headed arrow there. What we've proved is that way round. Let's try it the other way around. Let's assume that z is a real number. In other words, z is equal to x. And let's look at its conjugate. The real part's the same. Its imaginary part is the opposite sign. Imaginary part is 0. So we've got exactly the same as we had above. In other words, z is equal to z bar. So if z's a real number, it's the same as its conjugate. So this is another, this if and only if sign is equivalence. A complex number is its own conjugate if and only if that complex number is real. So they're one and the same thing. If you say real numbers, these are the complex, exactly the same as the complex numbers that are their own conjugates. So I'd now like you to use that result that z equals z bar is equivalent to z being a real number, and use that result to prove z bar is real. So stop the tape, stop the video, and see if you can prove that. Okay, how did you get on with that? We're looking at a complex number z times z bar. We're trying to show it's real. To do that, we'd have to show that its conjugate is equal to itself. In other words, we'd have to show that the conjugate of this thing is equal to itself, that we eventually get back to z bar if we find the conjugate of this. So we can do that. We have a product, z times z bar. We're finding the conjugate of a product. we've already proved that that's the same as the product of the two conjugates. So it's the conjugate of this part times the conjugate of this part. We've also shown that the conjugate of the conjugate is just back to the number z. This is z times z bar. So it must be real because its conjugate is equal to itself. The conjugate of z bar is z bar. So it must be a real number. So you've used all the properties of conjugation to show this result. There is, of course, another way to show it. If we let z equals x plus iy, then we know z bar is x minus iy, and therefore the product of z bar, x plus iy times x minus iy, will be x squared minus I squared y squared, which is plus y squared, and the imaginary parts cancel out. That's just a real number. So there's two distinctly different. This first method, you would say, is using the algebra of conjugates to prove the result. Second part, we're just going into the Cartesian form and showing that z bar is a real number, x squared plus y squared. This is a more explicit method of showing the result. But that's a nice way of showing the use and the power of conjugacy of complex numbers.